Okay, let me show you the contents of this video. First, I will introduce the discrete time Fourier transform, that is DTFT. Then I will talk about the DFT, discrete Fourier transform, and what is the need of it. Then I will talk about the DFT computation method. Then we will see that how DFT can be represented as a linear transformation. And then I will talk about the computational complexity of DFT algorithm. And then in last, I will explain the MATLAB code to find N-point DFT of any sequence. So let's go ahead. But before going ahead, I recommend you to watch my following video, which is discrete Fourier transform of images and image filtering. This video is actually about the 2D signals, images, where you will see the two-dimensional Fourier transform and its application to the image filtering. So this video will also help you to understand the concept. The link is given in the description, so you can watch that video. So now let me introduce the DTFT, that is a discrete time Fourier transform. So a time domain aperiodic discrete time signal, let's say xn, can be represented in frequency domain by its discrete time Fourier transform DTFT by this equation. So xj omega equal to sigma n minus infinity to plus infinity xn e power minus j omega n. Here xj omega is actually the continuous function of omega, which ranges from 0 to 2 pi, or you can say minus pi to plus pi. It means all unique frequencies lie in this range. Let's consider one discrete time signal xn, which has 8 samples, all are equal to 1. We can find its DTFT by this equation. Here we will see that xj omega, which is a spectrum of this Fourier spectrum of this signal xn, is actually complex in nature. So since it is complex, therefore we can find its magnitude, that means mod of it, and the angle, the phase spectrum. So just consider this signal xn, which has 8 samples, or all are equal to 1. And this is its DTFT spectrum, magnitude spectrum, which ranges from 0 to 2 pi. And this is the phase spectrum, that is the angle xj omega in the range 0 to 2 pi, right? Here we can see that this spectrum is a continuous function of omega, right? So now let's have some observation. So just by looking this magnitude spectrum, we can see that it is a continuous function of omega, which repeats after 2 pi. Okay, so this is a repetition actually. So after 2 pi, it repeats like this. So since it is a continuous function of omega, therefore we cannot use computers to compute this spectrum, because computers are actually the discrete machines with a finite precision. So computer cannot compute any continuous function. So to compute Fourier spectrum using computers, we can find only the discrete points of this continuous spectrum like this. So we can find some discrete points of this continuous spectrum. These discrete points of continuous spectrum are actually shown here in this figure. I have taken total 32 points in the range 0 to 2 pi. So you can see that from 0 to 2 pi, this is a continuous function of omega, but we are taking only the discrete points of this continuous spectrum. So we can compute these points with help of the computers, right? So since here the range is 0 to 2 pi and total number of points are, let's say, n in this range. So the gap between any two samples is 2 pi by n, and the kth sample can be accessed by this 2 pi k by n, where k is varying from 0 to n minus 1, right? So when k is 0, that means it is the first sample. When k is 1, it is the second sample, like that. So this process is actually similar to the sampling of this continuous spectrum in frequency domain. So, but what can be the maximum and the minimum value of these frequency samples? I mean the value of n. How many samples I can take, or how many points at least I can compute for this continuous function of omega. For maximum value of n, there is no limit, but for minimum, there is a condition. Because after taking these n number of samples or discrete points of this continuous spectrum, we must be able to get our signal back by inverse transform. So, in theory, it can be shown that if n is equal to or greater than signal's length, then by inverse transform, we can get our signal back from these n frequency samples. For example, if my signal xn, discrete time signal xn, has only 8 samples, as I have just shown in the previous slide, then the number of points should be either equal to 8 or greater than 8, so that xn can be achieved back from the samples of this continuous function using inverse transform. So, the general rule is this. Okay. So, your number of points which you will find of this continuous function of omega should be either equal to the length of the xn, or it should be greater than the length of xn. If you take number of samples less than length of xn, then what will happen? Obviously, when you take inverse transform, you will not be able to achieve your signal back. Okay. So, now let us see how the DFT actually evolved. So, this frequency domain sampling actually led to the development of the new formulas to compute the Fourier spectrum of discrete time sequence xn of length n by this equation. So, that previous equation is now modified to this equation. So, xk equal to n sigma n equal to 0 to n minus 1 xn e power minus j 2 pi nk upon n, where k is varying from 0 to n minus 1. So, that means you can find those n number of discrete values, or you can say discrete samples of that continuous function of omega of DTFT. So, this is actually your DFT formula, right. So, this is known as a discrete Fourier transform or N-point DFT. So, you can say what is DFT? DFT is nothing but it is the DTFT in discrete form. DTFT is a continuous function of omega, while DFT is giving the discrete points of that continuous function of omega, right. Similarly, I can find the inverse transform. So, xn can be achieved back by this equation. So, xn equal to 1 upon n, k equal to 0 to n minus 1 sigma, xk, these discrete samples or DFT values, e power j 2 pi nk by n, where n is varying from 0 to n minus 1, right. So, here you can see that DFT and IDFT, these two equations are almost same. The sigmas, I mean the summations and multiplications are equal in these two equations. Only the exponential is changing. Here you are getting the minus sign and here you are getting the plus sign. Now, let us see how the DFT can be represented as a linear transformation. So, the equation 1 of finding DFT can be written as xk equal to n equal to 0 to n minus 1 xn wn and k. So, here actually we took exponential in the previous equation. Now, I am representing that exponential by this wn and k. Similarly, the inverse transform can be represented by this equation. So, here the wn minus nk. So, what is wn? wn is actually the e power minus j 2 pi by n. So, wn nk means it is e power minus j 2 pi upon n power nk. So, that is e power minus j 2 pi nk upon n. So, that is same which is used in the previous equation. It is just another way of representation. And now we will expand this equation 1 for different values of k. So now let me put first k equal to 0. So when k equal to 0, my equation becomes this. So this is actually the xk. So k equal to 0, so x0. Sigma n equal to 0 to n minus 1 xn, wn nk. Right, so this is actually the nk. So k is 0, that's why this is n into 0. Now I will expand n. So I will put n equal to 0, n equal to 1, 2, 3 till n minus 1. So here you can see that when I put n equal to 0, I get x0 and wn 0, 0. Right, so this is n and this is k. Now I will put n equal to 1, so x1 and wn 1, 0. This is n, this is k. So simply varying n from 0 to n minus 1, 0, 1, 2 and n minus 1, right. So this is how I expanded n for k equal to 0. Now similarly I will expand for k equal to 1. So when I put k equal to 1, I get x1 and here you can see that nk. So this k is 1 and now I am expanding n equal to from 0 to n minus 1. So I am getting n equal to 0, n equal to 1, n equal to 2, k is same 1, 1, 1 everywhere till n minus 1, n equal to n minus 1. Now similarly I will expand for k equal to 2 and then I can do it for k equal to n minus 1 also. So all these n expansions I can achieve like this. So just see this these equations carefully. In all these equations you will find that x0 is here, x0 is also here, x0 is also here and x0. Similarly you will get xn, x1, 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 x2, x2, x2 and xn minus 1, xn minus 1 like that. Okay, and all these values are multiplied with these wn. So that means I can write these n number of equations in form of matrices. So let's see how. So I can write these n number of equations like this. So x0, x1, x2, xn minus 1 equal to this small x0, x1, x2, xn minus 1 and then this matrix. So just see the first equation, x0 equal to wn0 multiplied with x0 plus x1 multiplied with wn10, x2 multiplied with this like that and the last value multiplied with this. So you are getting the first equation. So first row is giving first equation, second row is giving second equation, third row is giving third equation and the last row is giving last equation like that. So those previous n number of equations can be written in this matrix form, right. Now I can simplify the powers. So this is simply multiplication. So 0 into 0 is 0, 1 into 0 is 0, this is also 0. So you can see that the first row is giving the power 0. Similarly the first column is also giving all the powers equal to 0. This one is 1 into 1 means 1, 2 into 1 is 2 like that. So this is how after a multiplication of these powers. Okay, so this is my matrix representation of those n number of equations. So this I can better understand with one example. So let's take, I can write these equations for n equal to 4. So n equal to 4 means I will have only those 4 equations instead of n equations and the coefficient matrix will be now 4 by 4 matrix instead of n by n. So this is how I can show you. So this is your xk for k equal to 0, 1, 2, 3. This is your input signal xn for n equal to 0, 1, 2, 3 and this is the coefficient matrix. So here you can see for all nk, it is very easy to write. So you just keep k equal to 0 in first row. So k equal to 0 you can see in first row and n is varying from 0 to 3, 0, 1, 2 and 3. In second row k equal to 1, right, k equal to 1 and n is varying again from 0 to 3. In third row k is 2 and n is varying from 0 to 3 and in the last row k is equal to 3 for all columns and n is again varying from 0 to 3. So it is very easy to write, and you can write any size matrix like this. Okay, so now after multiplying these powers, I will get this matrix. So first row having the all power 0. Similarly, the first column also has the power 0, and here you can see that there is some sort of symmetry. Here you are getting W42 and same W42 you are getting here. Like W43 you are getting here and W43 you are getting here. Similarly, W46 here and W46 here. So you are getting some sort of a diagonal symmetry in this case. And now let me show you that how we can find the values of these W's. Actually, I have already shown you that Wn is simply e power minus j 2 pi by n, right? So you can find any value of all these coefficients easily, right? So Wn is simply e power minus j 2 pi by n. Therefore, Wn 0, that means the power of this is obviously 1. Similarly, Wnn, that means the overall power n, the n will cancel out. So this is only e power minus j 2 pi, and e power minus j 2 pi is simply equal to 1. So you just expand this e power minus j theta, that is the cos theta minus j sin theta. So you will get this one. And this is one more relationship, the Wn n plus k equal to Wnk for this Wn. Similarly, there is another relationship, Wn n by 2 plus k is equal to minus Wnk. So with these relationship, you can find all these 16 values here. The first row and first column is easy because all having the power 0, so they are equal to 1. You just need to find only this. And also since we have the symmetry, so again the computation becomes easier. For example, W42 you have to find once. Similarly, W43 you have to find once, W46 like that. So let's see how. So W40, obviously because of the power 0 you are getting 1. So first row yellow 1 and first column yellow 1, all values will be equal to 1. Now let's see W41. So this is W41. So W41 is simply e power minus j 2 pi by 4, and that is equal to Wn. So from 2 this 4 will be cancelled out, by the 2. So this is e power minus j pi by 2, and this is equivalent to the cos pi by 2 minus j sin pi by 2. So that is equal to minus j. Similarly, you can find W42. So that is equal to e power minus j 4 upon 4. 4 will cancel. So that is e power minus j pi, and that is equal to minus 1. W43 is equal to j, and W44 I have already written Wnn equal to 1. So that is equal to 1, right? So now W46. W46 is equal to W42. How? Using this relationship. So W46 means I can write it as W4 4 plus 2. So Wn plus k is Wnk. So that is equal to W42, right? So W46 is nothing but it is W42. And W42 we have already found here, minus 1. So this is minus 1. So your computation again reduced. Now W49. So W49 can be written as W4 4 plus 5. So that is W54 by this relation. W54 can again be reduced to W4 4 plus 1, and that is equal to W41. And W41 is already found here, that is minus a. So this is minus a. So you can see that because of the these special properties of this Wn, our computations are very much reduced. So this is very suitable for manual computation. So now substituting these values of Wn in that matrix, we get finally this matrix equation, right? So we have computed all those values and we have put here. So this is the equation 3, which will be used to find the 4-point DFT of any sequence. So you just substitute your sequence values here, you will be able to find your DFT coefficients very easily. Simply you have to multiply these two matrices, right? So here this matrix is represented by the Tn, which is also known as a transformation matrix. So to compute a 4-point DFT of any sequence, you just need to multiply this Tn with that sequence. You will get the DFT coefficients. So this we can understand with one example. So now take one input sequence, let's say 0, 1, 2, 3. This is my discrete time sequence xn, and I need to find its 4-point DFT. So 4-point DFT simply I can find with this equation 3. So I have substituted the sample value 0, 1, 2, 3 here, 0, 1, 2, 3 here, and then simply multiplying these two matrices, I will get the DFT values. So I'm getting 6 minus 2 plus 2j minus 2 minus 2 minus 2j. So with this DFT as a linear transformation, you can easily see that how the DFT can be computed very easily. It's just an exercise of multiplying the two matrices. So now here we have the 4-point input. I mean xn was 0, 1, 2, 3, right? As I said, the minimum value of n should be 4. That means you can find the 4 samples of that continuous spectrum of xn. I mean the 4 samples of DTFT of xn. So that during inverse transform you can get your signal xn back. But as I said that n can have any maximum value. So suppose I want to find the 8-point DFT of the sequence xn, then how it is possible? Because your sequence is of 4-point only. So this is easy again. To compute the 8-point or even higher point DFT of this 4-point sequence, your transformation matrix will be of size 8 by 8 or n by n, right? And now input sequence has only the 4 samples. So you have to make it of size equal to 8, and that can be done simply by the 0 padding as shown here. So this is your signal of 4-point, and to make it 8-point you just need to pad 4 more zeros. So this is you can achieve with help of the 0 padding. Now let's see the inverse discrete Fourier transform. Now we can compute the inverse transform to get xn back by the equation 3a. So just write the equation 3a, xk equal to tn xn. This we have already written. So from this equation I need to find xn. So xn equal to, I will take tn matrix to this side. So that means we will get the inverse of this tn. So that means all the DFT values will be multiplied with the inverse of that transformation matrix. So you will get your xn back. But question is that how to find the inverse of this n by n matrix? Since n can be a large number, so it will be very difficult to find the inverse of that matrix. It seems at this moment now. But you will be surprised that it is very easy to find the inverse of this matrix, because this matrix is actually the unitary orthogonal matrix. I mean this T matrix is orthogonal unitary matrix, so its inverse is very easy. So you don't need any complicated computation. Just find the complex conjugate of all the elements of the matrix and divide by n. Okay, so for unitary orthogonal matrix you can find the inverse of matrix like this. So this is very simple. Finding complex conjugate is very simple, and then dividing all the values by n. So substituting this n inverse here in this equation, you will get this equation, which can be used to find the inverse of DFT. All right. So from DFT values you can find your signal back with this equation. So this is your actually DFT and IDFT equation. So here you can see that in equation 3 and 3b, the transformation matrix Tn is used. Tn is used in 3a, and Tn inverse, that means the complex conjugate of Tn is used in 3b. So it means your computation is further simplified. So that means you have to compute the Tn once. So you don't need to compute for DFT and IDFT differently. You need to compute Tn only once. For IDFT, you need to just find the complex conjugate of Tn. That's it. So your efforts are further simplified. So now let's do this example. So these DFT values we have already found in the previous slides. So simply substituting the xk, I mean the DFT value here. This is a complex conjugate of that Tn. You can see it was minus j and it was the plus j in Tn. So now the signs are just changed. I mean minus j is now plus j is now minus j, like that. Okay, and this is 1 upon n, I mean 1 upon 4. So when you multiply these two matrices, you will get your signal back 0, 1, 2, 3. So that was my xn, which I have taken in the previous example of finding DFT. So now you can see that finding DFT or IDFT is a very simple process of just multiplying the two matrices. So it means with help of the computer you can write the matrix multiplication program and you can find the DFT of any sequence. So now let's talk about the algorithm complexity. So just consider this DFT formula. So when you see this formula, you will see that to compute the n points of xk, you need total n square complex multiplication and total n into n minus 1 complex addition in this equation. So obviously the algorithm complexity is O n square. So for large value of n, this puts actually the too much computational burden on the computers, because it is there is an exponential growth of the computation because of the n square. So when you increase the value of n, the computer needs lots of time to compute these DFT values. Later, Cooley and Tukey propose a fast DFT computation method, which is known as the fast Fourier transform, FFT. This proposed method actually gives the n log n computational complexity, which is a huge improvement over n square. So this you can understand by this example. So suppose n equal to 1024. Your n square will give you 10,48,576. So that means the complex multiplication in DFT, the number of complex multiplication will be this 10 lakhs, only 1,048,576. But in FFT, this reduces to n log n. So n log n, which is on base 2. So 1024 is 2 power 10. So this is 10 multiplied with 1024, that is 10,240. So you can compare the computational complexity of DFT and FFT. So you can see that FFT is much faster than DFT. Okay. So in some other video, I will try to explain the FFT algorithm. So now let's come to the MATLAB program for computing this DFT. Here I am just implementing the DFT, not FFT. So this program will require the n square multiplications. So what I am doing here, first I am getting input from the user. So enter the size of the DFT. I mean you want to find a 4.8.164 points, 512 points, like that. And xn, input your xn. So you will enter the samples of your vector and then making a copy of it, finding length of this input sequence, and then finding number of zeros to be padded. Okay. So if there is a difference in number of points or number of samples or value of n and the length of the signal, then obviously you need the zero padding. So here zero padding is being done. Here we are finding Wn, that exponential e power minus j 2 pi by n. Then initializing the transformation matrix of size n by n. Then inside these two for loops, we are computing this transformation matrix T. So my T matrix is computed. So for any value of n, I can compute my T matrix. It can be 4 by 4, 8 by 8, 64 by 64, 32 by 32, like that. And here I am displaying one error message. If somebody enters n less than length of xn. That means suppose there are 8 samples in xn and you want to find 4-point DFT, which is not possible. So this will give you the error message saying n must be greater than or equal to length of xn. So that inverse is possible. Here I am finding the DFT because t is already computed and this is my signal, and here I have transposed xn dash, transpose because I have entered xn as the row vector, but I need the column vector so that matrix multiplication is possible. That's why it is xn dash. Now xk, I mean DFT values are known, and as I said, the DFT is generally complex. So to have the magnitude spectrum, you need to find the absolute values of those complex DFT values, and then for phase spectrum you need angles. So angle of xk. So by default this angle is in radians. If you want in degrees, you can convert that into the degree also. And now I am taking the inverse transform. So inverse transform is simply that formula which we have already discussed. That is 1 upon n t transpose. Actually t transpose will give you the complex conjugate, and then xk, your DFT value. So you will get your xnr, that is a recovered xn, and now just getting only the L values because other values after L, zero padding is done. So I don't know, I don't want zeros or padded zeros. I want only the signal values. So I'm just taking the first L values and then only the real values of that. And then these commands are used for plotting various signals. So this is actually my input signal. This is the magnitude spectrum, and this is the phase, and this is the recovered signal after IDFT. So this is a very simple DFT program which is capable to compute the DFT values of DFT and IDFT of any sequence. So you can try this for any of your numerical problem in your textbook. It will give you the answer, and it will also plot those spectrums. So now let me go to the MATLAB, and where I will run this program and show you that how you can use DFT values. So this is my program which I have already written. So I will simply run it by pressing this run button. Okay, so now it is asking me to enter the size of the DFT. So let me take the example which I have already explained you. So first I will take a 4-point DFT example. So size of the DFT, I mean capital N is 4. Now enter the input vector. So I will enter that vector which I have taken in problem. So that was 0, 1, 2 and 3, right? So just press enter. Now you will get everything as the output. So this is my input sequence. You can see 0, 1, 2 and 3, and this is the magnitude spectrum. So since I am computing 4-point DFT, that's why I will get only the 4 samples of that continuous spectrum of DTFT. So the first one is 6, and this is 2.828. That is the absolute value. If you remember, this was the minus 2 plus 2j. Okay, this is this is 2 minus 2, and in absolute it is 2, and this is minus 2 minus 2j, and its absolute value 2.828, and these are the phase values in the radians. Okay, and this is my recovered signal. So I'm getting my signal back 0, 1, 2, 3. So this is in graphical way. If you want to see the values, you can see here in the workspace. Just press double click this xk or type xk here, xk, this variable xk. It is containing all your DFT values. So here you can see that you are getting those same values: 6, minus 2 plus 2j, minus 2 and minus 2 minus 2j. So your numerical exercise is verified here. And if you want to see your transformation matrix, that is T, so you just type T, you will get those values. Okay, so you can see that the first column is 1 1 1 1 and first row is again 1 1 1, and this is your minus j, this is minus 1, and this is j, this is minus 1, this is plus 1, minus 1, this is j, minus 1, and this is minus j. So that is the same matrix which you have already seen in the slides. And now let me take one more example. So enter the size of the DFT. So let me enter the 64 and enter the input vector. So I will take the same vector 0 1 2 3, but now I will compute 64 DFT points of this 4-point sequence. So what will happen? As I said, to compute the 64 points, you have to pad this 4-point sequence with a 60 more zeros. Okay, so that matrix multiplication is possible. And the size of the T matrix will be 64 by 64 now. So in the previous example, it is 4 by 4 because we were computing only the 4-point DFT. Now my DFT size is 64. So the size of the T will be 64 by 64. Okay. So let me press enter, and here you can see this is my input sequence 0 1 2 3 4 samples, and these are 64 values of the spectrum, magnitude spectrum, and this is the phase, you can see. So when I increase the number of points here, you will get more smoother curve, or that will give you the glimpse of the DTFT, actually, the continuous function of omega. So I can also show you that. So let me try one more example. Enter the size of the DFT, let's say 256. I am taking too much size. Then enter the input vector. So here I am taking that square function 1 1 1. Let me take 8 samples 1 2 3 4 5 6 7 and 8, and then press enter. Okay, so this is the recovered signal after IDFT 1 1 1. You are getting out 8 samples, all 8 samples. And now let's see this one. So here you can see that this is your magnitude spectrum, and this is the phase spectrum, right? So more number of samples, more smoother the curve you will achieve, and you will have the idea of the shape of the DTFT also, right? So DFT is nothing but it's a discrete version of your DTFT. So I can also show the magnitude function with the continuous curve and these discrete points also. So let me run this program again, and the size of DFT, let's say 64, and signal I am using the same square function, and this is what I achieve, the 64 samples of the magnitude spectrum. So I will now plot these discrete values as well as the DTFT values. So I can plot XKM, hold on, and then stem XKM. Okay, so now see this one. So here you can see that this blue which is a smooth curve, that is representing the DTFT, which is a continuous function of omega, and these samples, actually 64 samples, are representing the DFT values. So now you will have the better ideas or relationship between the DTFT and DFT. Okay, so this is all about this video lecture. I hope you have liked it. So I really thank you all for watching this video. You can share this video to all other people so that they will also get the benefit. So thank you very much once again. Have a nice time.